Next, I'd like to call up Guillaume from our engineering board of advisors. Guillaume went to Cal here and studied naval architecture and marine engineering and has done a variety of projects in that field, most recently into using electroactive polymers as part of wave energy generation. And he's going to be talking about energy, sustainable energy from wind and waves.
All right, thank you, Petri. I'd like to thank the Seasteading Institute for having me here. I'm very happy to participate in this adventure. So I'm going to talk about wave and wind energy. In other words, we're going to talk about emerging solutions. So in 15 minutes, I can only give you a brief overview of that, but we'll try to keep in mind the basic methodology, basic rationale behind assessing a new solution from a technological and financial point of view. Why emerging? We'll see that wave energy is not yet an industry. There are hundreds of concepts out there. Some of them are good, some of them are bad. So there will be some kind of natural selection taking place really soon. Wind energy, on the contrary, wind energy is a sector. It's an industry, sorry. So things are reaching a plateau at this point, and my feeling is that we might see, as we change the external constraints, as we change the external conditions, you talked about evolution, Patrick, here we might see another kind, a new kind of wind turbine appearing. So I'm going to talk about that. And if we do have time, we'll talk about a third subject, which is very much related to the first two, which is storing energy using ammonia. All right, so when you look at new concepts, first of all, you must make sure you understand what you deal with. So waves, that's what people usually have in mind. Near shore, reef, surfing, good conditions. That's not what we want to deal with. It's more this kind of thing. So real offshore, fully developed seas. It's hard to get a sense of scale, so let's put a structure in there. This is really how it looks like in somewhat rough conditions. George can tell you more about that, but one thing you have to keep in mind when you want to put a structure out there, one of the first specification is a design life. Why so? Because it will drive the overall structure. It has to cope with fatigue, so there's a fatigue life. It also drives the maximum extreme conditions the system has to survive, right? And this has an impact on the capex, how much steel you're going to put, or whatever other material you're going to use. As a side note, there's a very good study conducted by Pelamis. We mentioned alternate materials, and it's a wave energy converter, and they looked at using alternate materials, so steel versus GRP versus concrete. And this was funded by the DTI, the UK Department of Trade of Industry, and the report is available online. Gives an interesting perspective on those solutions. All right. So waves looks pretty tough out there. So why shall we really care about that? Well, the main reason is that wave energy is a very, very condensed, concentrated form of energy, right? You do have solar energy. You create temperature gradients, which creates pressure gradients, and these create wind. And wind, through friction over the water, creates waves. In that process, you concentrate the energy. So that's interesting. Your system could, effectively speaking, be smaller and get a lot of energy. Let's put it, okay, the animations are dead, sorry. Okay, I'll try to illustrate that with using light bulbs. Just orders of magnitude, when you go solar, you got on average 100 to 200 watt per square meter. When you go wind, you're around 400 and 600. In 2 meter wave conditions, you got 5 kilowatts per square meter. That's very interesting. Here, I didn't have enough room to put enough light bulbs. This is the energy you get for a 4-foot wave kind of conditions. All right. Yeah, okay, I'm losing a lot of information here because the animation are not working. It's no big deal. Another way to look at wave energy is to talk about the power density per meter of wave front. And that's the one of the maps available out there. Anything yellow or darker than yellow is above 40 kilowatt per meter. To give you a frame of reference, outside San Francisco, we are around 20 kilowatt per meter on average, meaning you take 1 meter width of wave. Every year, you get on average 20 kilowatts over that meter. I work for the oil and gas industry most of the time, and to give another reference, if you convert that in terms of barrel of oil, just energy content, that's 200 barrels per meter every year. That's interesting, isn't it? So I'm not saying we can convert all of this, but that's a huge reservoir to tap into, and that's renewable. That's what I meant. All right. Okay, history. Long story short, it started very early on in 1799, first patent by a French guy. Real embodiment showed later in the 1880s. Interestingly, the two main locations where wave concepts were developed were in France, in Europe, and in San Francisco. There are two, it's very, very interesting. There are two projects that took place in San Francisco, another one in Santa Cruz. So this was a very crude approach, just converting wave energy into some kind of usable mechanical energy. Everything was going well, even reached some kind of first generation of electricity conversion using oscillating water column in the early 1900. And then something really wrong happened, fossil fuel. So it just killed all projects. To see wave energy showing up again, okay. Even the slides I try to hide to make the presentation shorter are appearing, okay. To see a new realm of concept showing up, we had to wait for the first oil crisis. Then the barrel of oil went down, the price of oil went down again, and so did the funding and the projects. But there are a lot of interesting things that happened. We had a much better understanding of the physics behind this, mainly the hydrodynamics, and this is something that we gained. So they have more of a spring mass approach. I won't get into the details, but basically most of the concepts that we see out there right now are based on the understanding we built in those years. All right, can you switch for me to the next slide? All right, okay, I'm losing animations again. Well, so if any concept you see out there should fall under one of those 9 categories. So we've got attenuators, point absorbers, systems using the pressure, the variation of hydrostatic pressure. All those 3 concepts react against the seabed or the marine system. For our applications, does it make sense? I'm not sure. It's going to be very complicated to attach that. When you look at the middle row, then it gets a bit more interesting. Especially the overtopping and the oscillating water column. I invite you to look at the report, Floating Breakwaters and Wave Energy Converter, published last year. It's available on the website. It's a very good introduction. And they mentioned those 2 concepts as promising. I fully agree with that conclusion. I'd like to add a few more things to it. I won't get into technical details, but as I said in the previous slide, all systems are based on the spring mass that can be summarized by a spring mass damper approach. Sometimes coupled, you've got multiple masses, multiple springs, and so on. But the point I'm trying to make is that all systems have a sweet spot, like a period at which they react well. That's a resonance period, right? And in order to have a system that is efficient, you need to match the wave periods, except that wave periods vary all the time. It goes from 4 seconds to 20 seconds, roughly. And it's very hard to modify that resonance, the resonance natural period of those systems. You have to tweak the mass, you have to tweak the stiffness, and so on. It's very complicated. When you deal with, and this is like, sorry, those two concepts, it's based on the bulge propagation and another one, the French bag. It's a deformable system with communicating, different chambers communicating all together. Or you've got the bulge propagation. This system has a much larger, what we call bandwidth. It has a multiple resonance, multiple modes of resonance, which means the system can react pretty well over a much larger spectrum of waves. That's something to keep in mind. And I believe The bottom one is being developed right now by AWS. They abandoned this concept fully after like 5 or 6 years of development and went for this approach. And I believe we could very much look at using this kind of technology on a floater. All right. And the other thing is on the bottom right, you see a variation of a point absorber, which is just using an array of those point absorbers. And then again, you no longer rely on one natural period. You can, by tuning them, controlling them adequately, you can increase the bandwidth. Okay, I'm trying to switch to the next slide. Ooh, here we go. So that's an example of the development going on. I won't go over that. I won't waste too much time on that. So the most adapted. When you look at a system, you must understand what constraints you have to deal with. We have no utility grid, meaning we need to be able to adapt the output, shut it down if necessary. We need to deal with the reactive power. Those systems usually use induction motors, meaning you cannot have what we call a black start. You need power to start it up. That's something to keep in mind, especially when you go to a larger scale. And ideally, you must be able to store the output. That's when we go to the energy storage issue. And as I said, must be kind of be more directly to the seabed, but must be attached to the to the floater. So that eliminates some concepts. On the right side, we will have eventually platform, and we will have a community. So the maintenance, operation and maintenance, can be done offshore directly, and this will have a very good impact on the OPEX. So, talking about money, as of today, I've participated in a lot of due diligences on the systems you saw before. I try to put that into a bracket. So I'm not giving names of companies, but that's roughly what we are looking at right now, and what most likely we'll be looking at for seasteading application. Because we won't be benefiting from the economy of scale. This is going to be like first of a kind or second of a kind. So that's pretty much the figures we'll be looking at, between $350 and $750 per megawatt hour. Still in the ballpark of what we've seen before, thanks to Melissa. Okay, wind. How much time do I have? All right, 1 minute. Okay. We're just going big. That's the end of the S-curve. It's time to change the realm here. When we go offshore, it has a drastic impact on the O&M cost. We try to go floating. Those systems require a lot of structure to keep it stable. Those systems don't like motions. So incorporating wind on seasteads will require a lot of attention in terms of motion, like George talked about. So let's look at an ideal system. You get rid of the unnecessary system. We want to go high, as big as high as we can, to get better wind, more wind. We want to maximize the foundation cost and so on. So ideally, we should get rid of what is unnecessary, and there's a great concept which is called high altitude wind. And this is based on basically having a kite or some kind of a plane attached, tethered to the generator. You got two approaches. One is having the generator on the ground, and you pull against the winch, and you can actually create electricity. Or the other obvious one is to have the generator, airborne generator, so on board the flying system. And the drawback of that is you have to carry the electricity down the cable, so it's a bit of a problem here. Anyway, that's something very promising, I guess. And 10 seconds on that. Ammonia can be used as fuel. It took place in World War II in Belgium. It has 1/3 of, in terms of energy content, 1/3 of diesel. Most recently, we had quite an interesting initiative taking place. A lot of people are working on that, and it's already happening on shore. So we convert green energy into fuel, and fuel is energy storage per se. That's something to keep in mind. All right, conclusions. As I said, energy storage is key Because if we want to look at renewable energy, except for oil tech, of course, the output is not constant, and you have to deal with it. You've got to store energy. There are a lot of synergies possible here, I guess. There are a lot of companies out there willing to have a test ground, willing to demonstrate what they can do, and the Seasteading could very much be perfect test bed for that. And yeah, we might just be the next catalyst for the new generation of technologies. Thank you for your time.